All right, here we go. Chapter 20. This is the last offline lecture of the semester on radioactivity and nuclear chemistry. So radioactivity is the release of high-energy particles or high-energy electromagnetic radiation from the nucleus of an atom. And so radioactive decay is when unstable particles spontaneously disintegrate in the nucleus and are released as radiation. And this follows first-order kinetics, just like chemical reactions. If we recall from Gen Chem 1 that the atomic number, or Z, is our number of protons in the nucleus, our mass number A is the number of protons added to the number of neutrons, and that our X is the element symbol, then we can write our elements and our mass numbers and our atomic numbers, and we can also write these symbols for the particles or subatomic particles that are released as radiation. Protons can be released, neutrons can be released, electrons, positrons, which have the mass of electrons but are positively charged, and alpha particles, which have the same mass and characteristics as a helium atom. Alpha decay is when a helium nucleus or an alpha particle is emitted or radiated from the nucleus, and this is the least penetrating type of radioactivity. You can protect yourself from alpha decay by shielding yourself with a piece of paper. A nucleus loses an alpha particle. That means that the atomic number decreases by 2 and the mass number decreases by 4. So 238 uranium would undergo alpha decay and split into 234 thorium and a helium nucleus. Beta decay is when an electron is emitted from the nucleus, and how that can happen is a neutron can turn into a proton, and a beta particle is about 10 times more penetrating than an alpha particle, so you need to wear heavy clothing to protect yourself from that radiation. And if an atom loses a beta particle, its atomic number increases by 1, but the mass number remains the same. Gamma rays are highest energy photons, and there's no loss of particles from the nucleus, there's just a release of energy. So there's no change in the composition of the nucleus, we have the same atomic number and the same mass number, but gamma rays are the most dangerous and penetrating type of radiation. We need lead plates, thick walls to shield from that. So some of the problem solving that we'll do in this chapter is to balance nuclear equations. So what happens to an element when it collides with some sort of subatomic particle or type of radiation, or when it releases radiation. We have 235 uranium colliding with a neutron to split into 138 cesium, 96 rubidium, and 2 more neutrons. We need to conserve the mass number on both sides, and we need to conserve the atomic number on both sides. As I said earlier, radioactive decay follows first-order kinetics. So we have our rate law, the rate equals, or our rate constant times the number of radioactive nuclei, and our integrated rate law would just be the natural log of the number of nuclei at some further time and the initial number of nuclei, and that equals to minus times the rate constant times the time. So our half-life for radioactive decay is also the natural log of 2, or 0.693 divided by the rate constant. Nuclear fission is a process that releases a lot of energy, and that's how our nuclear reactors are constructed to capitalize on this type of nuclear chemistry, and also atomic bombs are mostly made from fissile material. Fusion is another type of nuclear process where hydrogen atoms combine. 2 hydrogen nuclei can combine to form a deuterium nuclei, or 1 hydrogen nuclei that has 2 neutrons in it, plus 1 positron. And a positron, remember, is a particle that has the mass of an electron, but with a positive charge. And this gets us into the concept of matter and antimatter, so a particle that are the charge opposites of normal subatomic particles. So we have an electron as matter and a positron as its antimatter pair. Collision of matter and antimatter particles results in annihilation, where we convert all of that mass into energy, and that releases a lot of energy. And I will get into some more details about all of those things, and we'll do some practice problems, and then we'll be done with our lectures. All right.